This presentation is delivered by the Stanford Center for Professional Development.
Okay, hello again. I'll get started. So the topic that I want to talk about today is how to use classification methods in NLP. In particular, I want to start looking at the kind of discriminative classifiers that have been used a lot in recent NLP, and in particular in that space, what NLP people call maxent classifiers. And I'll eventually get around to explaining the reason for that name, but they may be more familiar to you as the space of logistic regression exponential model style discriminative classifiers. But before I get started on that, since I was in a little bit of a rush right at the end of last time, I just want to quickly kind of reorient us and think about this change of address email problem. And in particular, I think it kind of nicely illustrates what you can do with simple classifiers, which just assign things to one of a fixed number of classes, versus what motivates the kind of more complicated sequence models that are used a lot of the time in NLP. Okay, so the problem here was that what Nick Kishmerek and co. wanted to do was get out email change of addresses so that they could get, here is a new email for a person. And the way they set it up was to say, well, we can do this as simply two binary classifiers. And the first binary classifier just looks at the whole email and says, is this a change of address email or not? So that's just a two-way choice. And the way it does that, in the terms that we've started this course with, is you take a bunch of change of address emails, hand classified, and you build a language model from them. It could be your favorite kind of language model. It can be smoothed in your favorite way. You build a language model. You then take a whole bunch of non-change of address emails, and you build a language model from them. And so then you can ask, which of those two language models gives higher likelihood to an email? Is it generated with higher likelihood with the change of address language model or the all other email language model? And then if you add to that only one more factor, which is a prior probability estimate, an estimate of what percentage of emails are change of address emails, and you multiply in that weighting factor for the prior probability of having a change of address email, what you get out is what's normally called a multinomial naive Bayes classifier. But a multinomial naive Bayes classifier is exactly a class conditional language model classifier. So these things kind of do connect together. Okay, so then once you've made that first decision, the second decision is to say, well, in most emails, there are actually multiple addresses mentioned, and so which one is actually which one is the new address of the person? And the way that that's handled, and this has been a very common technique that's been used for a lot of problems in NLP, is that you effectively define a mini document, and your mini document is defined as, I think it's 6 or maybe it's 8, about 6 tokens to the left of the thing that you're interested in classifying, and 6 tokens to the right. So you've defined this little window, which is a mini document. And so then you ask for this mini document, does this mini document look like new email address? Binary classification again, 2 ways. Does this email look like new email address? Do binary classification. And if you're lucky, you decide that this one is the new email address, and then you've got out the right result, which is what's shown down here. And so these people made this system. They did a couple of different versions depending on whether the features were just words or made use of phrases. So in the better of the two systems, their message classification was extremely high, and deciding whether an address was a new address was pretty high, so they could do this task very well. Somebody asked afterwards, well, why do you need 2 classifiers? Why can't you just have one classifier that just looks at every email address and does the second classification task? And I think the answer to that is shown here, that making the overall decision on the whole email address, on the whole email, is much easier. And the biggest danger in this task is that you get killed by false positives, since most messages aren't change of address messages. And so you want to have as high an accuracy as possible at filtering out things that aren't change of address emails, and that gives you a fairly good take for doing that. Okay. So this looks really easy. All you've done is built 2 binary classifiers, and you've got an information extraction system ready to go. And the crucial thing to note, though, is what made it so easy. And what made it so easy was that candidate email addresses are deterministically identifiable by writing a regular expression for email addresses. So if you can write a regular expression that produces candidates, then, you know, if it's almost 100% accurate, you can just stop. If it's not quite that easy a problem, and you have to look in the context to see if it's the right one, whether it's the right email address, or in the earlier example, whether it's the right price for the product if you're shipping to the US, well, then you can use a probabilistic model as a simple classifier, where your probabilistic model just looks in the environment of candidates and makes a decision whether this is a good one or not. But a lot of the time, things aren't that easy for what we want to do. And the kind of examples that aren't that easy are the kind of examples I showed earlier in the last class when we're doing named entity recognition and we were looking for person names and company names and things like that. And we had that example where it was First National Bank of Ottawa or something like that. And there are all kinds of possibilities there as to whether it should be Bank of Ottawa or National Bank of Ottawa or First National Bank of Ottawa should be being recognized as the company name. And then when you're in that situation, you want to be comparing all of those possibilities off against each other. You need something that's considering different subsequences and their relative likelihood, and you can't do that with a simple classifier. Okay. Okay, is everyone good to there? Okay, so what I then want to go on to today is to start introducing discriminative classifiers and then lead from there into talking about how discriminative classifiers are used in the context of sequence models. So using this kind of discriminative classifier will be half of what you do in the third assignment, so we're kind of one by one working through all the assignment topics. It's also, I mean, I think these slides give a fairly readable introduction by themselves, but there are also then a couple of sections of Jurafsky and Martin which talk about using maximum entropy Markov models, which is the technology that we're building to here. Okay, so the primary contrast first off, and just sort of scene setting as to how this fits together. The things that we've started off looking at are what get called generative probabilistic models. So our language models that we did first, our IBM machine translation alignment models, or the naive Bayes classifier that I briefly mentioned, they're all generative models. And generative models are these models, I'll give some more details later, in which you kind of write this sort of probabilistic story about how the data is generated, and you multiply conditional probabilities together. And that kind of used to be the sort of state of the art that everyone used for all NLP problems if they're doing probabilistic NLP in the 1990s. But really, in this decade, a huge amount of the work that's been done has switched to using discriminative models. So I sort of want to spend a bit of time talking about discriminative models and how they work and how people build them. And this is kind of tries to be a little summary of why people like discriminative models. They work well. You get high accuracy. That's a reason to like them. Why do they work well? So I'll explain in more detail later. Really, the biggest reason why they're powerful and useful in NLP problems is that discriminative models, in some sense, are friendly to a non-techie kind of linguistically oriented data analysis person, that they actually provide a framework in which it's very easy to encode different sorts of linguistic knowledge and have someone else's clever package do the tricky number optimization stuff for you. So, you know, although there's sort of a certain amount to understand on how they work, at the end of the day, they actually kind of provide a sort of a very kind of friendly abstraction where it's easy to go about building these models without really understanding the details of how they work, providing you actually understand some facts about the domain and how to define features. Okay. So joint versus discriminative models. So joint models, which are generative models, that ultimately what they're doing is that they're modeling this joint probability. So that the joint probability of the data that you've observed and the stuff that you didn't observe, which is here, I'm calling classes with a C, but that's things also like the alignments when we're doing MP. And so those are these kind of examples we've seen. This was where we always told the noisy channel model story, which was Bayes' rule, where we were kind of, you know, doing a joint model and factorizing it one way and so on. Discriminative models actually sort of, in some sense, do something that's more obvious. I know we've spent kind of 4 weeks talking a lot about these noisy channel models and doing things that way, and maybe it almost seems natural to you now. But discriminative models say, well, there's something that you've observed. I don't care what it is. It's just stuff you've observed. What I want to do is predict the stuff that I didn't observe, and I'm going to directly build a model of this conditional probability. So I'm not building any model of the probability of D. I'm just directly modeling this conditional probability. So the difference for the MT case is, if we wanted to translate to French into English, we made a probability of E model and a probability of F given E model, which meant that implicitly when you multiply those two together by the chain rule, we had a joint model of the probability of E comma F. Why did we do that? Well, there's a sort of a halfway plausible story about how this lets you factor it into two problems, and each one was easier, and the language model could be reused, and there's a sort of a story there, which is sort of halfway believable. But you could just think, oh gosh, why don't we just make a probability model, which is the probability of English given French? That's what we want to translate from French into English. And so that's what discriminative models do. And so that then leads you into a space where there are methods like logistic regression, various kinds of exponential log linear sequence models, and also it's into the space of non-probabilistic models like SVMs and perceptrons. Okay. So this is what you get if you kind of have the kind of Bayes net picture of things. And so, I mean, I'm not sure I should spend a lot of time on this because probably this splits between the people who've already seen this a lot and therefore I don't need to review it, and the people who haven't seen it at all and therefore sticking it up won't be very helpful for them. But a way that a lot of people think about these kind of models these days is by drawing these kind of arrow diagrams where you have the nodes are the variables which take values, and the arrows are then showing the probability distributions that you're making. And so in the logistic regression model, you're just directly saying what's the probability of C given these data things, whereas for the generative model, you do this funny reverse story. Okay, so why would we be interested in doing conditional models? So, I mean, answer one is, you know, even if you change nothing, in general, conditional models do perform better. So you really can just sort of take a system that's exactly the same, if it actually has a knob on it, and say, switch it from being generative to discriminative, and it will normally go up a bit in performance. And so here's an example that does show this. So this was a classification task where it was classifying senses of a word. So whether Jaguar is the operating system or the big cat. And so just for this experiment, it was very carefully built. So it has exactly the same features were used for prediction. There was exactly the same smoothing that was done by having pseudo data. Everything was the same, and you could compare a generative model, which was naive Bayes, and a discriminative model, which was a logistic regression. And here's what you observe. If you look at the training set accuracy, the training set accuracy goes up massively, which should worry you a bit, because it shows that discriminative models can really, really easily overfit to data, which is something that we can talk about more later. But if we go to the test set, which is what we should be looking at, we see that the performance has actually gone up by 2.5%. So that's not so bad. You can just flip what you're doing from a generative to a discriminative model and have your accuracy go up a nice wad. So that's kind of a nice result. And you might think of the reason why that is because in a discriminative model, you're kind of making life easier for yourself, that you're only spending your modeling resources trying to capture exactly what you're interested in. So all you want to do in this word sense task is to predict the sense of a word in context. So if you only set yourself that goal, it's easier to do well on it. Whereas if you're building a joint model, that your joint model is actually trying to predict the distribution over all of the observed data. Things like how often different senses of word occur and what contexts occur around different senses. It's actually trying to model the entire data set. And so that means you're wasting a lot of your modeling resources on something that you aren't actually interested in evaluating. Okay. So how are we going to build these models? The way we're going to build these models in a lot of modern discriminative NLP is in terms of having features, and then we're going to put these features into classifiers. And so what is a feature? Here's the confusing slide that says what a feature is. Maybe I'll show the examples first. So here, the task I'm trying to do is part of speech tagging. So I have to aid, and I'm looking at the second word here, bit in blue, and maybe it could be a verb, or maybe it could be a noun. And so when I define features, I'm defining predicates over some little bit of my data, and my predicate is going to be, well, it's a function. It's going to be a function of some little piece of the data that will return a value. So here are some functions. So function 1 here says if the assigned class is noun and the word I'm classifying is lowercase and it ends with D, this is a Boolean function, it'll return true. Okay, so this purple feature is true of this data point, where I'm making the classification decision on the last word. It's also true of this data point, because the class is N, it ends in D, it's lowercase. But the purple function is false of these two data points. Okay, then my second classification function is that the class is noun, the previous word is to, and the previous part of speech was capital 2. So that function is true of this data point, but it's false of every other data point, including this one here, because here the class is verb. And so this is then yet a third one. So the idea here is that what I'll be able to do is actually kind of something like writing regular expressions. That you kind of can write these kind of tricky patterns of regular expressions to match different things. Here we're going to do exactly the same thing abstractly, but we're going to call them features. And so the way we'll be able to build good NLP systems is that we'll think of any useful facts about configurations that will help us predict part of speech, right? A useful fact to predict part of speech is that if the preceding word is a to, it's sort of likely the word after it will be a verb. Not necessarily the case, but all else being equal, a word's more likely to be a verb if it follows the word to. Right, so we take any kind of observations like that we think are sort of predictive of the classes that we're interested in, and we call them a feature. And so we write them down as a little function, which will evaluate to a value, and that's our feature. Yeah? No. I'll say a bit about that in a moment, but no, they don't. But before I say that, something that's important to note in practice, often very useful, is it's good to have not only features that are kind of indicative and are good patterns, but also to have features that indicate something is wrong. So it's useful to have features like the word is the, and you've tagged it as a verb. That's highly likely to be a mistake. And so having those kind of error features that would match if you've made a mistake is usually as or more useful than having features that match if you've done something correctly. And often they're kind of easier to define as well in tricky cases, that if you've got a kind of a halfway okay model, but it's still making some obvious mistakes, often the easiest way to address that is to look at how you can define some function that would match the kinds of errors the system is still making and that wouldn't match good examples where it gets things correct. And adding those features into a model will then enable you to make it better. Okay, so this then goes back to what are features. So crucially, features in general are a function that is a function of a piece of data and a function of the class that's assigned to that data. So they're looking jointly at both things. And so an arbitrary feature can be of this form, that you're taking, you're writing a function on the data and the classes and you're returning a real number. So no, they don't have to be binary or anything like that. And you know, in some contexts, this is very useful, and certainly you want numeric valued features of various kinds, and so that you might imagine in various kinds of web applications that, you know, knowing the size of a picture, which you might just measure in bytes, might be a useful feature. So in general, you can have arbitrary features. But it turns out that for a huge space of the NLP problems that we work on, that there isn't so much need for features that have real values. And so it's partly a simplification and it's partly other things. But in practice, if you look on the ground on what people do, the most common thing that you see in practice, and everything I present in these slides, is that all of the features are actually predicates which have a binary answer, that we're writing down some Boolean expression and we're saying, is it true or not? And so the features values are 1 or 0. And even more than that, normally the style of features that you see is that the feature asks some question about the data and then just says, and the class is noun, or and the class is verb. And so the interesting part of the feature is defined over the data, and then you've just got an equality check on the class. And so a lot of the time when people are talking about features, that they really only explain what they're asking about the data, and then the assumption is that you've then created features from this predicate, which is then saying, and the class is X, and you've produced X different features depending on how many classes that you've classified over. Okay. Okay. Yeah. Right. So yeah. So we want to find the class, but the idea is that, you know, we don't know the thing in blue. Well, a way to address not knowing the thing in blue, and essentially what we do is, let's try out every possible candidate. We know the set of classes, and then as soon as we're trying out a possible candidate and we're saying, okay, maybe it's VB, we can then evaluate a feature like this and say, that looks good according to this feature, or that looks bad according to this feature. Yeah, I mean, although this is, I think, first and foremost, having just these kind of features is sort of natural for a lot of natural language applications, like doing text classification or part of speech tagging or name entity recognition or word segmentation, that really these are all the natural kinds of features. It's perhaps also worth noting out that noting that restricting your features to this form actually makes things considerably more computationally efficient, because since everything here has a 0 or 1 value, that means that when you're actually implementing things, you can kind of simplify the implementation because you're just sort of adding the active features rather than having to do extra multiplications and stuff. Okay. Right, so we have these features that we can then apply to data, and the idea is to each feature we're going to give a weight, and the feature's weight is going to be its vote. It's going to say, this is good or this is bad. So our features here are saying that if we're assigning the class noun and the preceding word is to, which is part of speech tag to, you know, that's sort of possible, so we're going to give it some weight as an okay thing. So maybe we give it a weight of 0.3. But really, if the preceding word is to, it's more likely that it's going to be a verb. And so we're going to give that a higher weight, 0.7 or something like that. And we're going to use the weights of the features as voting for a particular class. And so what we're going to do is look through all of our features that match in a certain configuration. And so features are then kind of votes before or against a certain class assignment. And so we're going to tally up those votes, and we're going to decide which is the most likely class assignment. Okay, so features assign a weight, and then so that when we're building our models, we're going to be building our models to optimize our classification accuracy. And crucially to do that, we're going to use these two quantities. Firstly, any feature has an empirical count on our training data. So we're assuming hand-classified training data to build the model off. And the empirical count of a feature is, well, we just take all of our data instances and try out our feature and see if it matches, i.e. is true on them, and we get an empirical count for the feature. We get that, okay, this feature matched 13 times on the data. And I'm falling into the language here of assuming that all my features are binary, but you can generalize the non-binary count case and still work out the expectation. Okay, and then what we're going to want to do is build a model. And the model also assigns some expectation to a feature in the usual way of expectations. So the model is going to be working out how likely different features are, and so we have a model expectation for a feature. Okay, so I'm going to come back to fairly soon how to start building these models, but let me give a few examples first of just sort of showing the kind of places and how these kind of models are used. And so introducing these ideas of features and classes. So a very simple case is text categorization, which is equivalent to logistic regression in a simple case. So here, our features might just be particular words, and the class that we want to assign is one of a number of text classes, so business, sports, world news, etc. If we do word sense disambiguation, we effectively do that kind of like text classification. We define a mini document around a word of interest, just like for the change of address example, and then we then have a context like this, and we then ask questions about that context. And the questions might, again, just be bag of words questions of, is the word restructure nearby? But commonly, we can also then ask more precise questions. So we can ask questions like, is the next word debt? So we have kind of richer classes of features that we can ask about. And then the more interesting case that we'll work towards is doing the more typical kind of problems, which commonly get called sequence problems. And the way we're going to handle sequence problems is effectively we're going to walk through the text and we're going to handle the sequence problems one position at a time. So at any particular point, we are kind of going to build a classifier assuming that we've already done everything up to a certain point. So our picture looks like this. And what we're going to be wanting to do is build a probabilistic model over which part of speech we should put above the word fall. And so the label is the choice of a part of speech, here noun. And then the kind of questions we can ask is, well, what's this word? What's the previous word? What's the previous part of speech? We can also ask about what's the next word, because all of the data is assumed to be observed. The things that we can't ask are about following classes, because we haven't yet figured them out yet. Okay. And so here are just a couple of slides giving a few results on tasks and motivating some of the properties of this. So this is a simple text classification result, which is a paper from Zhang and Oles. I guess Zhang was a Stanford SCCM graduate. So they're doing text classification over this Reuters data set of news articles, which is a very classic text classification data set. And they basically compare a number of different classification algorithms, and here are their results. So naive Bayes is kind of a classical text classification baseline, and it's kind of what everyone presents as their baseline for text classification. And on this data set, it's getting 77% F1, where remember from last time, the F1 is doing this harmonic mean between precision and recall at the class level. And honest people like to report text categorization results using this F1 measure for the classic information retrieval reason. I mean, a lot of the time in those machine learning papers, they don't do that. And you'll just see accuracy results for text classification. But I mean, those results tend to be extremely misleading because typically you have a very skewed distribution of classes in text classification problems, and you can get high accuracy results even if you always or almost always get lots of the small classes wrong. So that doing F1 evaluation is a much more rigorous measure as to whether you're actually doing a decent job at getting rare classes right. Okay, so naive Bayes here got 77% F1. Not terrible, not great. And then here are three other systems. And they all get about the same, as you can see. So something that's sort of interesting. So all of these are using bag of words features of what are the words in the document and are throwing them into building a classifier. And the thing that's sort of a little bit interesting here is that any statistician would tell you that doing a linear regression over this categorical count data of word occurrences and documents is, all of the assumptions of the model are wrong, you shouldn't be doing it. Whereas in some sense, the assumptions of the naive Bayes model are right. It is the right kind of categorical model to be using for building text classification problems. But the result that you actually seem to get is if you build a discriminative model, it works much better, and it kind of almost doesn't matter which one you choose. It doesn't even matter if it's one that's supposedly highly inappropriate for the problem in terms of its assumptions, and that all of them work a lot better than the generative model. And one of the things that they talk about again, and that I'll get back to, is this question of how to avoid discriminative models overfitting. Okay. Maybe I've sort of kind of said this by this point, that because I kind of went through an example of the part of speech tagging, but this is perhaps more clearly illustrating how we're up to a particular point in making our decisions, and the kind of features we can use are what's the current word, what's the next word, what's the previous word, what's the previous tag. We can then also ask about joint features, and commonly do. So what's the sequence of two previous tags might be a useful joint feature. And then commonly we can kind of define a lot of domain-specific, interesting and useful features. So while asking about the word is useful, it has this problem that words are very sparse, and a lot of the time you won't have seen words or won't have seen them in a particular context. So a lot of the time you can get a ton of value by defining your own equivalence class features, like does the word have a digit in it? And in some sense, you could think of this as an extremely large, well, infinite, I guess, disjunction over words, right? Of is the word 2 or is the word 3 or is it 4 or 5 or 22.6? But in practice, using hand-designed functions that pick out domain-useful classes of data items is just a highly useful technique in improving these kinds of models in practice. And it's one that's kind of, I think, typically underexploited by people. That people who build NLP systems and get them to work well spend a lot of the time thinking about how they can hand define good features that will pick out things just right. Whereas if you just kind of throw in the most obvious features of what's the word and what's the tag, in practice the systems sort of work, but not so well. Okay. So this kind of discriminative modeling, you can kind of apply it to any other kind of problem as well in NLP, and essentially people have. So sentence boundary detection, what do prepositional phrases modify, lots of different things. Okay, I think I've sort of said that, except for the bottom bit. Okay, so I've sort of said twice what joint and conditional models are. The next important thing to know about them is how easy are these models to make. Notwithstanding if you're having some troubles with assignment 2 at the moment, in principle, doing joint models over categorical data is really easy and it's really fast to build models. And that's because it's a theorem that optimizing joint likelihood over categorical models is just using relative frequencies. You count and you divide and you've got the maximum likelihood model. Conditional models turn out to be much harder to do because optimizing conditional likelihood, you can't just count and divide. So you have to do iterative methods of numerical optimization, and I'll get onto that. Okay. Yeah, so these kind of ways in which we're building features and collecting votes brings us into the space of what are called linear classifiers. And linear classifier is kind of a useful notion to have because really most of the machine learning methods people use most of the time are different forms of linear classifier. So the picture for a linear classifier is you have features, you want to assign some class, each feature has a weight, and the way you work out which class to choose is you work out a vote for each class, and the vote for each class is you see which features match on a particular choice of class and the observed data, and then you take the weight of that feature and you just sum up these votes. So it's, if you have binary features, it's literally as easy as this. Okay, for toAid, it can be tagged as either a noun or a verb. Let's just say there are only those two choices. And for the features I had before, these two features match it being noun tagged. This feature matches it being verb tagged. So if these features have the weights shown, the vote for it being tagged as a noun is minus 0.6, because I just sum those two numbers. The vote for it being tagged as a verb is 0.3. 0.3 is bigger than minus 0.6, therefore we tag it as a verb. That's what a linear classifier does. All linear classifiers do that. And, it's not actually such an advanced thing to do, really. So all of the trickiness beyond that comes down to how exactly do you choose these weights. And then there are a bunch of algorithms that choose the weights in different ways. So one of the simplest algorithms of linear classifiers is perceptron algorithms, which effectively do this online learning to nudge weights around until you stop making mistakes. SVMs are linear classifiers in the basic case. They do a different kind of optimization. But what we're going to do here for exponential models, which have a whole bunch of names, log linear, maxent, logistic, Gibbs, etc. models, what we're using to set the weights is that we're going to set the weights so we maximize the conditional likelihood of this exponential model form. So we've chosen this particular exponential model form, and then we're going to say, okay, we want to fiddle these lambdas so that we give the highest conditional likelihood possible to the observed data. Okay, well, what is this model form here? Well, one way of thinking of it is sort of the following kind of crude way. Well, we want to be building a probabilistic model. And what we have is features with weights like this. Well, the first problem we have is that these things can go negative, right? Because if you sum these two, minus 0.6, that's bad for a probabilistic model. And so one way to solve that is we exponentiate. Because if we exponentiate, everything's positive. That sounds good for a probabilistic model. Then, you know, for probabilistic models, you want to normalize, right, and turn it into a probability distribution. The way you do that is by considering different classes and working out the same quantity for them, and then just dividing through. And behold, you have a probability distribution in 2 easy steps. So in some sense, you can think of it as no more complex than that. There is a lot more motivation for why this exponential model form is a natural and good form for modeling these kinds of decisions, but I won't get into that right now. Okay, so what we get, once we have this model form and features that give votes, we can then get out a conditional probability over class assignments. So using my previous example and the same active features, that we had the two features weighted 1.2 and minus 1.8 voting for noun. So we take the sum of their votes and exponentiate it, e to the minus 0.6, and then for it being a verb, we're taking the vote for that, e to the 0.3, and then for both of them, we're dividing through by the same normalization term, which is just the sum of this plus the sum of that, and we do our little bit of math, and we get out that this model is saying it's a 29% chance that a noun should be assigned and a 71% chance that a verb should be assigned. Okay. Does that make sense up to there? Okay. Right. So anyway, so that's the model class that I'm going to talk about and that we're going to go through the math of and you're going to use for the assignments. You know, it's a very standard, commonly used, good way of doing things about it, doing things. It's absolutely not the only way to do it. So, I mean, for instance, another model class that there's been a lot of work on recently in machine learning is using support vector machines, which setting those weights in a different way to optimize a different criterion. Another good way to do things. I'm not going to do them in this class. Okay, something that's worth noting is that, you know, for my picture here of saying, okay, this is our exponential model, we've got features and we're putting weights on the features, that actually a naive Bayes classifier is actually an instance of an exponential model. So for the naive Bayes classifier, the probability of a class given a data was the prior probability of the class and then the product of the probability of each observed word, if it's something like a unigram model, given the class. And then again, we'd have a normalization term where we consider all different classes. And so, well then, if you do a little bit of math on that in particular, you kind of put in these X-log pairs, and that you assume that your features are log probabilities rather than just probabilities, that behold, what you get out is that that model just becomes the same exponential form where your features is the word dishwasher in the document, corresponding to the probability of dishwasher given the class, and then your weights are then the log probabilities. And so naive Bayes is just an exponential model. And so then the question of how do they differ comes down to this question of how are you choosing to set these lambda parameters. And well, in a naive Bayes model, you are setting the lambda parameters to maximize the joint likelihood by setting them to the observed conditional probabilities in the data, perhaps with some smoothing. Whereas for what we're going to do now for discriminative classifiers, we're instead going to set these lambda parameters so as to maximize the conditional likelihood of the decisions that we're going to make. And so that leads into these next couple of examples in which I hope to not confuse you and instead to show you these insightful, wonderful examples that these things are different and do deliver different results. Okay, so what we have here is we're going to be sensing whether it's sunny or raining. And we're assuming that we kind of have a not very good noisy sensor outside our window which attempts to sense whether it's sunny or raining. And it's not very good. So the sensors make mistakes. In fact, they only get things right 3/4 of the time. So if it's raining, it's going to say plus 3/4 of the time. And if it's sunny, it's going to say minus 3/4 of the time. Okay, so that's what the sensor is like. But then for this example, there's an extra bit of art in here, is let's suppose I actually only have one sensor outside my window, but there are 2 wires running from it. And I wrongly think I've actually got 2 sensors outside my window, but they're both wired together and actually report the same thing, always. Okay, so the configurations I can then get is that the sensors are, my 2 wires, when I measure them with my little whatever, are both going to be saying the same thing. And so if it's raining outside, the 2 things I can get is plus plus, which I will get 3/4 of the time it's raining. And if I assume here that overall it's raining half the time, this is assuming we're in Seattle or something, I guess, then 3/8 of the time this is my observation. Similarly, 1/4 of the time when it's raining, they don't detect it and they return minus. So that data overall happens 1/8 of the time, and then the reverse over here. Okay, so my naive Bayes model factors are half the time it's sunny, and if it's sunny, it'll report, plus 1/4 of the time and minus 3/4 of the time. If it's raining, it'll report plus 3/4 of the time and minus 1/4 of the time. Okay, and then what I want to do is work out what probabilities my naive Bayes model predicts, given that I see plus plus. And, well, if I see plus plus, looking at this picture, it's obvious what it should predict. Because, in the cases where we're getting plus plus, it should be predicting that means that 3/4 of the time it's raining and 1/4 of the time it's sunny. That just is the observed data, right? So it should report that the probability of rain given plus plus is 3/4. But what I'm doing is measuring the sensor twice and I'm assuming that my two wires are independent measurements where they aren't really. And because I'm making that wrong independence assumption, my probabilities come out all wrong. So that the joint probability of plus rain is the prior probability of it being raining a half times the probability of plus given raining is 3/4 times 3/4. And I work out the other cases, and I actually end up way overconfident. The probability of raining, given that I see plus, is 9/10 according to a naive Bayes model, and it's only 1/10 chance of being sunny. Does that make sense? Okay, so that's... Now you might say that this is a very artificial example, but what I'm going to want to argue is that it's not an artificial example. I mean, yes, this is an artificial example, but the problem it's illustrating isn't an artificial example. It's exactly how things are in NLP all the time, right? So the problem is if you have overlapping evidence, so you're measuring things multiple times that aren't actually independent of each other, there's this systematic problem with generative models like the naive Bayes model, that naive Bayes models multi-count the evidence. So that if you're trying to measure things that are correlated or overlapping or something, it will treat it each time as independent, and it will count the evidence many times. And so crucially, what Maxent models will do is that they'll solve that problem, as I'll get back to in more detail later, that a Maxent model will work out how to adjust the lambda weight so it's not multi-counting evidence. So that all I showed so far was an example where the naive Bayes probability estimates were wrong. And you could just think, well, so what? The probability estimates weren't that good. But does that cause problems in practice? So here's a further example, which is kind of cooked up in the same way, but it illustrates how making these false independence assumptions does actually cause you to make the wrong classification decisions. Okay, so this time we're at an intersection and we can see two traffic lights. We can see the traffic lights on these two sides. And so there are two possibilities. There are three possibilities. So the traffic lights could be working, and this one could be green and this one could be red, or they could be working and this one's red and this one's green, or the traffic lights could be broken and they're both showing red. And let's assume that this is the real data distribution, so that 6/7 of the time the traffic lights are working, and when that's true they flip back and forth, and so half the time each, i.e. 3/7 of the time each, you're getting this configuration and that configuration. And then 1/7 of the time, the lights are broken and you see this configuration. Okay, so what we have here is that this light and this light, their behavior is correlated. But let's assume we were building, again, a naive Bayes model and that we treat those two lights as separate pieces of evidence. So then we have a prior probability of the lights working, and then we have the probability of each light being green or red conditioned on whether the lights were working or not. Okay, so the probability of working is 6/7, and then given it's working, you're equally likely for each light to be green or red. So you get these probability factors. Probability of broken is 1/7, and then if it's broken with probability 1, you're seeing a red light. Okay, and now here's where things go broken. If we build that naive Bayes model and then we show it two red lights, well, what does it do? Well, what it should do is look up here. If both lights are red, you should conclude that the lights are broken. But that's not what a naive Bayes model that models the two lights separately actually does. So what we find is the probability of broken red is the probability of broken is 1/7 times the probability of red given broken is 1 times the probability of red given broken is 1 equals 1/7. Whereas the probability of working in red is 6/7 prior probability of working, then a half chance of seeing red given working times a half, which equals 6/28. And if you do your math, this number is bigger than that number. And so what the model actually predicts is the probability of working, given that you see red is 6/10. And so therefore the classifier will return working when you see red. Okay, so that's bad. So because the naive Bayes classifier was sort of set from these generative relative likelihood probabilities, that, you know, it is a theorem that these probabilities are the ones that optimize the likelihood of the observed data within this model. But that actually causes it to make the wrong classification decisions. And so the idea that motivates discriminative models working better is, well, why do we have to choose the relative frequencies if all we want to do is get classification decisions to be right? Suppose we just change the numbers, could we then get the things to work out right? And we could. Like, suppose I just changed this one factor arbitrarily because I felt like it, and said, let me change in my model the probability of broken to be a half. You know, that's not true in the observed data. That wasn't the right answer. But suppose I just did it anyway. Well, then I'd get the probability of broken red being a half, and the probability of working red being an eighth, because I've just changed these numbers. And so now I'd predict, if I saw red, that the lights were broken, because there's only a 1/5 chance of them being working. And so by fiddling the numbers, I can cause a classifier to make the right discriminative conditional classification decisions, because I've stopped saying I have to be modeling the joint likelihood of the observed data. Okay, and so in precisely that way, you can improve your classification decisions by not staying true to the observed data likelihoods.
Would you have messed up the probability of red, green, probably broken red, green,
No, you can actually work through it. If you make this change, the model now predicts correctly in each case. That if you give it red, green, it predicts it. I mean, it's kind of obvious because since this is 0, if you give it an input of red, green, or green, red, it says with probability 1 that it's working. And now, if you give it red, it says with probability 0.8, it's not working. Okay. Okay, so this is sort of just a summary of where we're up to. So to build a Maxent model, we do kind of effectively linguistic data modeling, and we define what are good features. And then for each of the features that we're going to want to give them a weight, and we're going to want to give them good weights. And so to give them good weights, what we're going to use is the count of the feature on the training data. That's its empirical expectation. And then we're going to want to work out a model expectation so we can work out the data's conditional likelihood according to the model. And what we're then going to want to do is fiddle those weights with no other goal than to improve the conditional log likelihood of the decisions given the data. And that quantity at least seems closely related to the classification decisions that we want to make, and so we hope it will work well. And so the next major part of this, which I'll get into as far as I can today, is, well, how do we go about setting the weights? Okay, well, the way we go about setting the weights is we have to do some math. Okay, so what we want to do is we want to set these lambdas so as to make the conditional likelihood of the classification decisions as high as possible given the data that we have. And then, as is usual, we actually maximize the log conditional likelihood rather than actually the likelihood because you have more summations that way, and so life is easier. Okay, so that's the log of the product over the individual classification decisions in our whole data set, which is the sum of the log of the individual classification decisions in our whole data set. So this quantity here, well, we know what that is. It's just the log of this exponential model form that we wrote out before. And, I mean, we can calculate this for any particular feature weights and any functions and data sets. Is this easy to calculate? Just a note as we go by. In practice, whether this is easy to calculate or not depends on how many possible classes there are to assign. You know, it's fairly easy to calculate this because you're assuming a particular observed class and observed data set. This is the supervised training data, and you kind of work out which features apply, sum them up, and exponentiate. The thing that's potentially a killer is in the denominator, you have to consider here summing over all possible class assignments. So in practice, if the number of possible classes is small, like you're classifying email messages as spam or not spam, you haven't got a problem. But if the number of potential classes is extremely large, you've got an enormous problem. And so, I mean, that's one of the reasons why, to this day, almost invariably, language models are built as generative models. Because if you start thinking, well, can I use this technology we're learning about to build a discriminative language model? Well, the problem is that in a language model, you want to predict over what word comes next. And there's a huge space of possible words. And if you have higher order features, it's an even huger space of bigrams and trigrams. And so then trying to calculate this becomes completely infeasible, certainly by exact inference. Yes? Yeah, so it turns out, I mean, it turns out that that's not a problem in general. I mean, you know, like everything, like all of these things, we can buy our machines with lots of memory and so on. But in the typical case, that's not actually such a bad problem. And that comes back to when I said you make it a lot easier for yourself computationally if you have only binary features. Because, you know, the typical situation that you have is that the total space of features is very large. So a lot of the time in kind of good NLP discriminative classifiers, the total space of features might be, you might have 5 million of them, say. You might even have more. But most of those features are very specific to particular contexts. So in a particular context, the number of features that actually match is typically very small. It might only be 20 or 30, because most of the features are saying things like the word is circus, or the previous word is housing, and the word before that is cheap. You know, so they're very, very specific features. So normally, you know, almost none of them match in a particular situation, and so there are very few that match. And so that means you can do this efficiently, providing you can quickly find which features match in a particular context. And that's where you can then start into your computer science tricks of doing clever indexing so you can very efficiently find the features that match. Whereas there kind of isn't any solution for that here, because if you're doing it over all classes, well, you're doing it over all classes. Okay, So we want to fit all the lambdas to maximize this log conditional likelihood. How can we do that? Well, we can separate, since this is a log of a whatever division thing, we can separate it into two parts. We can have the numerator part minus the log of the denominator part. And notice then kind of the numerator part is just considering our observed data. Okay, so well, how are we going to maximize the lambdas? At this point, it's a numeric optimization problem. We want to set those lambdas so that this number gets as big as possible. Okay, so that means we do differentiation of this and say, okay, let's differentiate this and see if we can get this. Well, let's differentiate this and see if we can find the maximum. And the maximum will be where this quantity equals that quantity. So, wait. So the derivative of this quantity equals the derivative of this quantity. So you're at a maximum of the function. I almost said that wrong. Yes. I'm trying to maximize it for my supervised training data. So I'm working out this quantity, which is all of my supervised training data. So I have some big set of data, capital CD, consisting of individual data points with classes assigned to them. And that's the outside summation here is over all of my data points. But for all of them, I have observed answers. Okay, so I do differentiation. So doing the numerator is really, really easy because, well, you have the log and the x next to each other, so they just go away. And then you have a partial derivative. So you're working out partial derivatives with respect to each lambda I, each weight in the model. So the partial derivative with respect to lambda I goes to this summation. So you can move the partial derivatives inside the summation. And then, since you're doing the partial derivative with respect to lambda I, the only thing that remains is what is the thing that lambda I is multiplied by, which is this feature fi of cd summed over all of your data set. And so the derivative of the numerator is this empirical count. How many times did the feature match in the observed data? Okay, the derivative of the denominator is vaguely more tricky because you have to remember the chain rule. I guess that's why they have these math requirements in engineering. So we want to differentiate the denominator term, and so then we have to have, okay, we want to differentiate this log of something, so we use the chain rule. So we take the derivative of the log is the inverse, and so you have the 1 on the rest of it times the derivative of the inside bit, and then you do the chain rule a second time, and you have the derivative of exp is exp, so you have the exp of the rest of it times the derivative of the inside, and then for this derivative of the inside bit here, that's the same as before, that the partial derivative with respect to lambda I, everything goes away apart from fi of the class down here. And then lo and behold, if you stick this bit over this bit, you get back exactly the model form that we had for the exponential model. And so what you end up with is that you're summing over all of the data points in your training data, but then you're summing for every possible choice of a class decision at each point, the probability that the model assigns to that class decision times the feature, which again in our case is just this 1-0 decision. So this is saying, well, what's the model expectation, i.e. the model's predicted number of times that this feature should match according to the data. Okay, so what you're actually doing, right, so your derivative is how many times the feature actually matches on the data minus how many times the model predicts the feature should match on data. on the observed data that you've given it. And so therefore, to maximize the conditional log likelihood, you want the derivative to be 0, and so therefore you're wanting to make the actual count of a feature equal to the predicted count. So in the optimization that you're actually doing, you've measured the empirical counts of every feature on your training data, and then you're trying to fiddle around the lambda weights. So the model expectation, the model saying, okay, according to my model, this feature should be firing 7.2 times. It's actually firing 6 times on the observed data, so I have to fiddle down the weight of a feature so that I'm predicting it fires less times. Okay. So that's what we want to do. Theorem, the optimum, doing this, so this is a nice, as I'll come back to next time, this is actually a nice problem. It's convex, so you can find an optimal answer, which is the best weighting of parameters. It can be under constraints, so the actual weights might not be unique, but there is a maximum to the conditional likelihood that you're assigning. And here's a neat property that the maximum always exists as this, providing you play nicely, providing you just count true feature counts of observed data. You have to have a well-formulated problem that has a maximum. If you start trying to play tricks and say, I don't like what it's doing, so why don't I just change a few of the empirical counts that I observed in the data, then you can very easily make your model constraints inconsistent, and then there'll be no solution. Okay. And so I presented these as effectively exponential models, and in terms of what I've presented, they've just been exponential models. Despite that, in NLP, these are always referred to as maximum entropy models. But I think I'll leave till next time actually getting into sort of saying why those also get called maximum entropy models. Okay, so at the end of the day, what we have is we have these weights, and we want to set them so that we maximize the conditional log likelihood of the training data. So at this point, the conditional log likelihood is a convex problem. You can set the lambdas. You can find the maximum. So you can do it with any numerical optimization method. And there are just then questions as to which numerical optimization method you use. I mean, there was a in traditional work in statistics and NLP, people tended to use these generalized iterative scaling methods or iterative proportional fitting style methods. They're basically, although I still have them on the 2 slides there, I mean, they're basically abandoned these days because everyone has found that you can do things much more efficiently using more general numeric optimization methods. And so if you've done that kind of stuff, you can think of things like conjugate gradient methods or quasi-Newton methods. If you haven't done that kind of stuff, don't worry about it. We're going to give you an optimization package, which is a limited memory quasi-Newton optimizer. And these kind of optimizers are essentially basically the state of the art for doing optimization of large-scale discriminative learners of this size type. Where in particular, the trick is all in this limited memory bit here. So quasi-Newton methods in general construct the Hessian, which is then you've got this matrix of partial derivatives. And the problem is that that's completely untenable if you have 5 million features. And so all of the trick of limited memory ones is that they're trying to approximate that while using a much more reasonable amount of storage. Okay. I think it sort of makes sense for me to stop here today, since the next bunch of slides then go into the motivation from the angle of maximum entropy, and it sort of doesn't make sense for me to have done one of those slides and then stop. So I'll call that enough for today and then move on to the second half next time.